Femtosecond laser fabricated Nitinol living hinges for millimeter-sized robots. Millirobots are currently limited by existing materials, and creating new materials and fabrication techniques is one of the 10 grand challenges of science robotics. Nitinol has useful properties that have the potential to improve many different aspects of millirobot design. By rastering away sections of nitinol, like for the hinge shown in the figure on the left, we can create monolithic, multifunctional structures, significantly reducing the manufacturing time of robots like M-Clary on the right, which is manufactured with a stack laminate process. This process requires cutting multiple materials and heat pressing them together, leading to a much longer manufacturing time than cutting from a single material. However, nitinol is susceptible to heat-affected zones and work hardening, which degrade material properties, so many traditional machining techniques like long-pulse laser cutting and manual machining cannot be used. Nitinol can be processed using various techniques such as abrasive jet machining, focused ion beam milling, and photochemical etching, but these processing techniques typically cannot produce 2.5D and 3D structures. Femtosecond laser machining is fast, can produce complex structures, and cold ablates the material, evaporating the material before it can heat up so there are no heat-affected zones, as shown in the figure below. Our multi-step manufacturing process begins with a grid of rastered cuts on our custom femtosecond laser micromachine, in which we vary laser power and the number of passes. Next, we obtain the height data from a confocal microscope. Finally, we used a MATLAB script to create graphs comparing etch depth as a function of number of passes and laser power. We selected 200 kilohertz repetition frequency and 5 passes for our parameters as a trade-off between material quality and manufacturing time. We evaluated our laser parameters 4 different ways. First, we compared the cross-section of a manufactured hinge to the theoretical cross-section and found they matched up well. Next, we performed an X-ray diffraction analysis to confirm that the femtosecond laser did not alter the underlying crystal structure by transforming austenite into martensite, which would degrade the nitinol's superelastic properties. We then measured the roughness using our confocal microscope and found that the roughness of the manufactured nitinol is not significantly increased from the bulk material. Finally, we performed a fatigue test on our nitinol hinges and found they performed similarly to previous works. To model the nitinol hinges, we used a standard bilinear material model, which matches well with the actual nitinol stress strain curve shown here. This bilinear model was used to create 2 models for the living hinges, a theoretical model for only rectangular hinges and a computational model for rectangular and notch hinges. After experimental characterization, we found that the models closely predict the torque profiles of the hinges. Thus, we can use these models to design hinges with specifically tuned torque profiles dictated by application requirements. To demonstrate the usefulness of strong, high-displacement hinges for certain millirobot applications, we made a 4-bar wing mechanism. We tested the wing mechanism at various frequencies and found a maximum peak-to-peak stroke amplitude of about 50 degrees at 200 kilohertz, which does not exceed the elastic limit of the nitinol hinges, but does exceed the elastic limit of the typical material used for these hinges, Kapton. Thus, optimizing the transmissions could lead to longer lifetimes for these robots. Key contributions include accurately manufacturing 2.5D nitinol structures for certain millirobot applications and creating a computational model that can be used for designing high-precision devices.